Item 5, Scituate Reservoir mitigation models and infestation. Sony, welcome.
Thank you. Sorry for the delay.
Okay, Sony's been with us for a while, but
Kids bake every Friday, so. Is there a pointer or something that I could use? Or?
doesn't seem to work. Didn't seem to work.
Maybe we should just go in front. Oh yeah,
That's
it's not going to work.
There we go.
Oh, just a clicker.
I think that's
Just a clicker.
Oh, you did one.
That's fine. I'm good.
Sorry.
No, it's fine. It's not going to work anyway. I don't think
You don't think? Okay.
Good morning, everyone. My name is Soo, and I'm assistant professor in the Department of Geosciences. I'm a water quality modeler, hydrologist. I have my student here, Sophia Paul, who's largely involved in developing a Scituate Reservoir mitigation model. And so this is what we're presenting here, part of our work, not entirely everything. So the team consists of Tom Boving, myself, and Sophia, and I have a few undergrad students who've been helping out here and there with data. I'm not going to go into too much detail about Scituate Reservoir. You all are familiar with the reservoir and you know, like some of the details already. What I'm going to talk here is the safe yield, you know, like, and then how that's projected to be changing with the flood, you know, like extreme events and drought in picture. So the background of the study, you know, that where did we get this idea of doing this work is basically from, you know, Scituate Reservoir being like the primary drinking water reservoir for state Rhode Island, and there are many events that have caused flood downstream, but the event in particular, which we're talking about, the 2010 event, have had some serious impact downstream, and so our goal is to model, you know, use physically based, semi-distributed operational model to quantify what happened during 2010 through modeling effort, and then predict, you know, like change some of the variables within the model to feed in extreme events and see how these would change if the rain were supposed to happen in a different time of the month, or you know, like if the intensity of rain is different, if we were to you know, mimic the most recent Hurricane Florence, like what would the outcome be? So we did some of those simulations as scenario analysis, and that's what we'll be presenting here right now. Some of you have seen these slides many, many times. Like here, Kathy, seen them before. So we have various objectives here. What I'm going to highlight here is basically the second bullet that you can see, improve inflow predictions of Scituate Reservoir mitigation model and propose operational rules. In a sense, like, you know, this would be nice. This is what is going to happen if we were to, you know, see the flood of this extent. So that those are basically scenarios that we're showing in this talk. We've also done some of the additional work relevant to this project, which is combining climate change with land use, and to see, like, you know, like how if we were to increase the low density residential area within along the Scituate Reservoir watershed, what would the outcome be in terms of like the 2010 flood? We're still repeating that flood event to see, like, you know, if let's say we add more houses, like low intensity development houses along the reservoir area, what would that high pulse event look like? So we did that, and it's already been published in Lake and Reservoir Management Journal. We also worked on forest dynamics. When I say forest dynamics, we're not going into single tree kind of study, but it's the gypsy moth infestation that created havoc from 2014 through 2016, and had some issues in 2017 too. So we looked at, like, what kind of hydrological changes do we anticipate if these kinds of, you know, like insect infestations happen regularly, and then, you know, whether or not that would have an impact on water quality eventually that goes into the Scituate Reservoir. So that's our work in progress right right now. So the highlight for today's talk is going to be mostly about this work, but it's not going to show. Mostly looking at the safe field aspect. So some of the model details that, I'm not going to go into the nitty-gritty details of the model here. If you have questions, Supriya is standing right here. She might be able to explain the physics and the subroutines within the model. But what we did here in this case is a particular study is there are multiple inflows that go into the reservoir, and we need to have a good inflow characterization to know how much water goes into the reservoir before we start modeling reservoir. So there are many ways to do it, and we've used a few different approaches. What I'm showing here is a physically distributed, semi-distributed model, SWAT, which is largely used worldwide and is able to account for different sources, and you can also discretize it at define a scale if you want. So we use SWAT to predict inflows that we do not have like gauges for. There are many rivers that are not gauged. So we used gauged rivers and then used those as a proxy to run SWAT, recalibrated model against those gauged rivers, and then we predicted inflow for the ones that do not have inflow, so are not gauged. So what we did was, and then we used those inflow and fed into an OASIS model. OASIS doesn't have any, it's not an acronym, it's OASIS, it's water and desert. I'd want to give it an acronym to it, but there's none. OASIS is an operating model that has been largely used by big water operators. New York City Water Supply System is one of them, and I have had working experience with these models when I was in DP before coming to URI. So it's the operation model, mostly focused on. It could be linked with water quality model to do all kind of water quality study. That's what New York City Water Supply System does. It's not just water quantity. They're concerned turbidity, so they have a lot of focus on turbidity. For this particular purpose, we not deal with water quality at all. It's mostly just water quantity, and so it's a standalone OASIS program. It's a hydrologics product, and put a little link down there. Hydrologics. This is basically a mass balance kind of model. It's if you really go into the details of what went into the model, it's not that difficult. It's basically what went in and what went out and what's being stored. That's what it is. If you have that, which means if you have your input variables correct, you will have your output variables and output, nicely predicted too. So that's where we're trying to focus on getting our inflow predicted well, so that what goes into the reservoir is correctly captured. So with the output that came out of the OASIS model, what we did was we manipulated the model to mimic extreme events like flood events. We even created a scenario of Florence, and then we did drought scenarios. We changed vegetation patterns to see how that kind of impact on the reservoir dynamics. Just to give you a little insight to what the reservoir in general, would look like. And this is not different from what Scituate Reservoir looks like. So there is a bottom area where sediment accumulates, and it's called the dead storage, where you cannot really have much water extraction happening. There are different levels of intake pools there. There's a maximum pool level, which is at the saturation. There's normal pool level, which is where most of the water, like the upper intake would be. And then there is minimum pool level, which is basically close to lower intake in most reservoirs, and it's good to not get to that point. So this is a conceptual reservoir diagram that we essentially pulled out from the map that we received from Province Water Supply to show where the lower intake level is, and then where the upper intake level is, what's the reservoir capacity, at what elevation reservoir is at full capacity, and then reservoir is operated with flashboards. And so like when you have flashboards on, what the elevation would be. So it just gives you a pictorial diagram, information on what, how the reservoir, Scituate Reservoir in particular, looks like. Please feel free to ask questions. So, I am pretty sure nobody can read this. So this is basically to show like all kind of data that went into the model, and just to give you an insight to the length of data, special length of data, temporal length of data that we have. So demand data, demand of plant influent, daily, we have daily data that we receive from Reservoir Supply. We also receive monthly data from them, and thanks to Reservoir Supply here, you've been very, very helpful. Then we have, so precipitation data, we have these precipitation data coming from co-op stations, and we also use PRISM, which is this remote sensing data, satellite data, to make sure that we have rainfall and temperature data at 4 kilometer grid spaces. So we actually have those data already stored in server for general use now. And release from the gate, which is again Reservoir Supply system data. Most of these did come from Reservoir Supply. Release from overspill, flashboard data. So it gives you that, like how long data do we have. So to the left, I see it. Data stuff from 1975. Okay, so yeah, so 1965. Some of the data go back to 1965, like flashboard data, precipitation from the satellite, and also the master co-op that goes all the way back to 1985. And then there's certain data that starts from 1975. So no reservoir system is fail-safe, but we can help to make it better. It's always, there always can be a certain kind of disaster that could fail reservoir system. There's always a risk of running out of water. Our study, that's the reason why we need to study what is it that can cause, the total failure of the system, or what can cause complete run out of water. So water supply planning and operation, this is where, wise, like management and operation comes into play. They can reduce, but might not eliminate that risk completely. Many operation systems in the US, the large operation systems, such as New York City, New Jersey, they have forecast-based operation, and they do use this OASIS model. Some people use Riverware. In fact, New Jersey also moved to OASIS now. They use forecast-based system operation, and then do positional analysis. Positional analysis is basically when you watch Weather Channel, you see these spaghetti plots showing different models, model projection, and the one that might be the best one. So that's basically what the positional analysis is. It can allow you to manage risk exclusively and effectively. There are a few other ways that risk could be reduced. Like can we expand capacity? Again, these are some of the questions that might not be applicable for Scituate Reservoir, or might be. Smart operating policies, right? So how do we operate matters. And then all of these have something to pay. So you're willing to pay for it to get to achieve these level of reliability, or whatever we not propose, but the alternatives that's available. Now, when we talk about reservoir, most of the time it's spoken in the language of safe yield, and that's what the focus is going to be here. So, what is a safe yield? It's the amount of water that could be safely drawn out of the reservoir during some specific drought. So, when I say specific drought, specified drought, sorry, it's mostly the drought of record. So, if we're going to go back to the Rhode Island law, when this, which helps define safe yield, it means drought of record. So in our study, drought of record is 1960s drought. So we want to make sure that that's being captured. But safe yield could be studied in many different approaches. It could be, again, a safe yield of record, which would be the drought record. It could be 50-year safe yield period. It could be 20 years too. So our study could even be considered as either safe yield of record or 50-year safe yield, right? So you could fit in both. So what is the safe yield from reservoir and how is it impacted? So what's the maximum rate that can be withdrawn from Scituate Reservoir without emptying the reservoir? It all depends on what the stream flow is. So I'm emphasizing here, it's important to have a good characterization of inflow that goes into the stream, which means you also have a good characterization of the precipitation event in order to have a good understanding of reservoir volume and how it changes. And the critical event in the history that helped determine how big the reservoir has to be is largely drought. So, safe yield, like if you're considering the drought of the year record, then I think it would be it'd be okay to say safe yield is safe. But if you're considering something different as your safe yield study, then you might get a different safe yield value that might not be safe enough. So system operated and historical safe yield will run out of water in any worse drought. So if your drought is worse than the historical drought, then the chances of running out of water is high. So these are just certain examples that we're giving. Like safe yield is studied in many different ways. Safe yield for reservoir is different than safe yield for groundwater. So and then the calculations are different too. So safe yield operated at 20-year safe yield will run out. So when you say 20-year safe yield, that means there's a possibility of running out of water on the 21st year. So in order to reduce the risk, as I said, I'm emphasizing in operations here, increasing water available during drought increases liability. So how do we do that? This is something that requires a large coordination among the water suppliers, stakeholders, states, and like many parties here. Operations of all facilities can substantially increase the water available during drought, which means, like in this case, in the Scituate Reservoir case, there's not many reservoir to link, but if you were dealing with a large reservoir system like New York City water supply system, which has 12 reservoirs, 6 in west of Hudson and 6 in east of Hudson, in order to be effectively distributing water during a drought period, they have to have a lot of conjoint operations, and they have to move water from, Catskill to Delaware to the Kensico and so on. So, in our case, it's fairly straightforward. The objective of such operation is basically, making sure that there's no water losses through spills or seepays, and I believe there's not much increase of Scituate Reservoir again. So these are some of the information that we received through, mostly through the literature review and the reports that Flum's Water Supply have published in the past. It's the gross safe yield of Scituate Reservoir is estimated to be 92 million gallon per day based on the 50-year recurrence interval, which is basically that 1960s drought, taking that into consideration. And assuming that the minimum water elevation is 216 feet in the Scituate Reservoir to provide hydraulic flow. So there are a few other studies that have been done. There was a report that was produced, and Mr. Collins, I do not know who he is. The report showed a slightly lower 89.31. Here you can correct me on these values. Based on a period which is 1916 through 87, it still covers that 1960s worst drought. So what we're trying to do is we're trying to come up with similar number, not drastically different number, using a newer approach to see if it is safe to like go beyond 92 million gallon per day, and whether it is going to be okay to release more than 9 million gallon per day, that environmental flow that's required to be released downstream. So the graph here, it's not, I'm going to read what the x-axis and y-axis is. So the graph on the left is it's the storage versus elevation. In fact, both of them are storage versus, so the bottom is surface area versus elevation. The top one is storage versus elevation. And it's primarily showing what the maximum storage area is and at what elevation the maximum storage is. So if you look at that blue curve, and then a lighter line that you see, so that the line on the top on the left figure is the maximum storage, which is at 37,000 million gallon, and the storage, the elevation corresponding to that storage is 286.12 feet. So this is again just giving you some general information about the reservoir and what the elevation maximum storage area and volume is. The bottom picture on the right is the picture showing surface area versus elevation, and what's basically showing is at that elevation, the same elevation, 286.12 feet, with the maximum storage is, the surface area is approximately 5.3 square miles. So, again, I'm not going to go into too many details of how safe yields are calculated. We used a few different approaches. We used OASIS model to calculate safe yield. We have mass curve analysis, which is the historical way of calculating safe yield, and we also did sequential analysis. So we used a few different methods to calculate safe yield, and each method gave slightly different values here. So what I'm showing here is also not just the historical safe yield, as we calculate, but also applying climate change scenarios to these safe yield and see how that would change. So the x-axis is a time slice, historical time slice, that's 1960 to 2018. RCP 4.5 is radiation concentration pathway of 4.5, which is the climate change scenario based on CMIP 5. RCP 4.5 is, like equivalent of low emission, carbon emission scenario. RCP, and then we also have, we do not have the other scenarios in here, but we also ran the model to mimic high emission scenario, which is RCP 8.5 scenario. And we have time slices here, and this is how most of the climate studies are presented. So 2 time slices, 1 time slice showing a projection from 2020 to 2060, second time slice of 2061 through 2100. So most of the studies, and again, the climate change studies, this is how people present their work. So what do we see here? OASIS model was basically showing less uncertainty in historical data. Like if you see that box plot, the box plot is much thin for the green box, which indicates that there's less uncertainty in our estimation using OASIS model. Other 2, sequential and mass curve, sequential peak algorithms basically showing slightly high safe yield, but if you look at the median, that black line in the box plot, it's showing about similar range. When we put climate change into context, it ends up, we do see increase in safe yield for all the situations, both using mass curve, OASIS, or sequential. What does it mean? It's basically showing that receiving more precipitation, and that's what the climate change projection shows, and that relates to, like increasing the safe yield predictions too. Now this is a similar plot, which is basically showing historical river monthly mean inflow. So water that goes into the reservoir and how that's projected to change at the monthly basis. So the orange color bar plot is historical. Then you have the green one, which is 2020 time slice. If you go back, remember what I showed in the former slide. It's exactly the same time slice. And then the violet color is 2071 to 2100. And what's important here is to see like how each of these months are showing potential increase in inflow that goes into the reservoir. And like if you put things in relatively so, except for April, right? In April, it's actually the scenario is actually showing decrease, so we have to check that. And then the rest of the months you can actually see, like month of November, there is huge increase in inflow for the climate change scenarios. And just a snapshot here to show how the reservoir elevation look like for April month. We do have these for other months too. April, we put April here because immediately after March, March peak flow event. How do reservoir respond to the not the low flow situation immediately after the spring runoff ends. So what this showing is reservoir from mid 70s to current. What you can see is reservoir has never gone down to the extreme, like a volume. It's like the lowest it has gone is it's still above 272 feet. And this bar chart is just to show how many times, number of days the reservoir in fact has gone over that 286.12. So if you remember, that's the maximum reservoir volume, 37,000 million gallon per day. It's showing that you can see there are a number of days every year. There are actually 1985 doesn't have anything, 1981 doesn't have anything, 2014 doesn't have anything, but then there are many times that reservoir have gone, stayed above that that maximum reservoir volume that we're talking about. So here, there's a lot of details in this picture. X-axis is all kind of models that we've used. Definitely will be cumbersome to go over everything here. There are 41, so CME3, which is the earlier climate change models, there were 140 models, global climate models, which had a lot of uncertainty. So CME5, the most recent product, they clarified a lot of uncertainties, and so they ended up now having only 41 models. And out of that 41 models, we did not intend to use all the 41 models. It's of no use using every single model. So what we did was we picked 8, right? How many models? 14. All right. So 14 models, which are largely used for Northeast. So the basis for picking these models. And then we ran our safe field projection for each of these models, and each of these models are saying some different story. And the reason is, each of these models some of them have precipitation showing high, some of them are showing low. I mean, none of them actually show precipitation lower than historical. All of them do have above historical rain, but they're all everywhere. And that was one of the reasons why we created an ensemble of this 14 models, and then we ended up making this.
Go back to the next previous slide. Is there any explanation of why there's a steady increase in days that the reservoir was above the max?
Okay, so the line that you're seeing, the slope.
Yeah, it looks like it's.
Well, so we just wanted to show whether or not we can see any trend in increase. So it could directly lead to the high inflows if we try to relate that to the precipitation. One way to look at this would be to put a precipitation graph and then a number of days and see if we see correlation, the increase of precipitation leading to increase in inflow, thereby leading to higher number of days. And once again, so what we do not have here is we're just putting this cumulative number for each year. So some of them, you know, like if we tease this out into months, it will be even better. So, you know, there might be precipitation, monthly precipitation only in March of month where we see it increase, or month August when we see high increase, and we do not see anything in November. So if we split this into month, you might not see that steady increase. You might see, you know, like you might not see any trend at all. Does that explain?
Yep.
Some of the other things that we looked at was, you know, like how would the demand change, and this is again the model-driven model results that we're looking at. Like if we were to increase drought by certain percent, what would happen to the demand, you know, relative to the existing operating rule? And this is just for 1 year, and the x-axis is Julian day 1 through Julian day 365. And what you can see here is, you know, like there's a relative increase, and the pattern is pretty much similar to the existing rule because we did this consistent increase in demand, like 5% increase everywhere. So, which in reality, that does not happen. So if there is demand increase, then there are certain time of the year there's high demand. So if we put that in picture, you would probably see a little different curve here. And how does the usable storage at Scituate change? Again, these are all scenarios that we're developing. So 10% increment, 10% increase in demand relative to existing operating rules. So the one that is at the top, which is green line, that is existing operating rule. If we are following that operating rule, and how does usable storage change? So again, we're showing 1 year snapshot example here, 2002, 2003. I'm showing like when does the demand increase, and when does the usable storage increase relative to the demand, and how that is impacted if we were to increase demand by a certain percent. So this is a quick scenario that we produced for you know, immediately after Hurricane Florence happened. What if this were to come our way? How do we, you know, respond? I mean, is there anything that we need to know in terms of hydrology, in terms of reservoir operation, if this magnitude of hurricane were to head our way? So just to give you a general information on how much precipitation was received during Hurricane Florence. So precipitation in inches is the y-axis. The x-axis is giving you the month that happened, Hurricane Florence. So it's starting August 1st through, we have October 24th. Blue line is precipitation, which comes from Wilmington, North Carolina, and then the red is Providence precipitation. And so if you focus on the one that has the highest peak, that was when Hurricane Florence hit Wilmington, North Carolina. So if you look at the amount of precipitation that looks familiar to 2010 precipitation is close to 10 inches. And then this is an inflow scenario that we're still kind of revising, trying to figure out why it's going down that sharp. So this is a draft form that I'm showing you. On the x-axis, the same period of time that I showed you before, starting August 1st. Actually, this ends 9/30, which is September 30, and the discharge that it produced. So the y-axis is discharge in cubic feet per second. So what's showing is with Hurricane Florence, the inflow going to the reservoir was 4,500 cubic feet per second. Is that correct? For a particular scenario. again, we are revising this to make sure that this number is correct, because when in March 2010 flood happened, the inflow was a lot more. Reservoir response during Hurricane Florence. These are scenarios we brought. What we did was we pulled out precipitation data from Wilmington, North Carolina, and we replaced it for Providence just to create a scenario. So, the atmospheric effect and ocean circulation, all those things aren't in play, or wind isn't in picture here. So it's just precipitation. And what you can see here is the reservoir inflow chains. So the bottom, the blue line is the exact line that I showed you before, which is inflow, and then how that has impact on the reservoir elevation. So with that kind of inflow, with that 10 inches of rain, immediately there is a lag of a day there. We have to figure out what's happening right there. The reservoir elevation is 286 within 1 week.
They say that it takes 1 week.
Here, right there.
Yeah.
1 week. Yeah.
Takes 1 week, yeah.
1 week to rise above the sluice gate.
Yeah, and above that maximum elevation. So there are a lot of extra information here. I'm gonna probably have to skip this one. Just to aware you of how these kind of reservoir operations are done dynamically in other part of the other places like Potomac River. They use this dynamic reservoir operation, and again, it's not just for water quantity. They're also using this operation for water quality. Like New York City Water Supply System has alum treatment requirement to deal with turbidity, so they need to get forecast, short-term forecast frequently. Kansas River, there are many others too, not just this. So what we did was, we will be wrapping this project in May, early June, and we will have quite a comprehensive report. This is just a section of the report that I'm presenting, showing all the work that we've done, the model details, everything that goes into into each of the models that we presented here. But we also came up with sort of like potential solutions. It's not what model has predicted, or it's not model suggested. It's something that we think that these are some of the solutions that we could use to operate reservoir effectively. So short-term solutions would be, how do we manage reservoir? I think Conceptual Water Supply has already proactively been managing the reservoir. I mean, last year March, when there was a big the 4 nor'easters back to back to back, I was definitely very much worried because it looked very much similar to what happened in 2010. But you guys had a very good collaboration with National Weather Service, and you had this proactive management already in place, which is great. There are other things that we're thinking of, like other solutions. Instead of the flashboard, toothed flashboard, maybe a V-notch releasing might help. And then also by increasing historical release of water from currently 9 million gallons per day to certain value, which we did some simulations to come up with those numbers too. And then in the long term, which is more of a hydraulic structuring stuff like retrofitting spillway, automated gates, or even selling water to commercial areas and so on. So those are some of the long-term solutions that we think might help the reservoir. And we have a lot of other proposed research that could be a segue to what we are currently doing, like post amendment on safe yield. Again, all these comes with legal liability. What does that mean in terms of legal aspect? Quality of water, right? If you are storing water for too long time, then that A's matters. And when you're treating water, if it's too much A's, that builds a lot of carbon, and if you're treating that water with high concentration of carbon, then it could lead to formation of disinfectant byproducts. like trihalomethane, haloacetic acids. Rhode Island does not even have a regulation on NDMA yet. I mean, my lab is working on NDMA concentrations for these Rhode Island source waters. And so, this water has nitrate, and if you're treating, you don't even have to treat with chloramine, in the case of high nitrate or ammonium, like water. So A's matters. So water quality would be of concern if we are thinking about keeping water too long in reservoir. Hydropower generation, definitely. If we are thinking of this long-term solution of siphoning or, like a lot of hydraulic structures, then hydropower generation could be something that would be of interest to everybody. Operation rules, once again, operation rules could be applied for water quantity, for water quality, depending on what's needed. And all of these would require some sort of feasibility analysis in terms of whether or not it's even feasible or how much would it cost to really do this kind of sort of study or even implement them. And then sea level rise impacts, which is basically we haven't even looked at the bad flow and how much of it is a concern. We don't know that yet. So that should be it.
Thank you. Questions from the board?
I think you said that the climate change models that you showed were the low carbon emission versions?
The one that I showed is 4.5 RCB is the low carbon, low emissions. We have 8.5 also.
And does the general pattern change?
The pattern, so there is increase for sure because we're talking about like precipitation. I do not have a figure here, but if we put the monthly one, remember seeing the box was the monthly one, the pattern will change with 8.5. But in both the cases, higher, it goes to the higher extreme. And none of them are showing low water, like less inflow. So none of them are really showing any signs of drought. Everything is pointing towards flood.
So what's your time frame for wrapping your full
So
study
we are revising the draft report right now. Plan is next 3 months we should be done with this. And what we're planning to do is once this report, which is going to be a mixture of scientific and non-scientific results and all, we will also put together a white paper, which would be more of a, distribute to everybody kind of white paper and easy to read.
So you'll be making specific recommendations to the management?
Sort of suggestions. I wouldn't say like, there's a difference between recommendations and suggestions. You put in a public policy perspective. So alternatives sort of like, this could be done, and and we'll also point to certain examples from like other states or other water authorities who have used these methods. That way we're not just devising them.
And it's management suggestions for drought as well as for flood
Yes,
control.
both.
Great.
Just a question, you mentioned stream gauges, so was the inflow data strictly based on the streams that had gauges, or?
So the streams that have gauges are used as a calibrate, to calibrate our model. And so the model is developed in such a way, it's a big watershed model which has streams.
So you're accounting for the other streams that aren't gauged?
So based on the ones that we have good data, we calibrate the model, and then we predict for the ones that don't have, that gauged data.
As far as the releases that you talked about, is that a minimum regulatory number right now, or is that something that you can actually?
The 9 million
that they
gallon.
can, not you.
9 million gallon per day. So that's the minimum release.
And it's a regular.
Yes.
It's a regulatory number. So, but we are also, showing that in terms of climate change. So if there is an increase in inflow and the, potential increase in volume of the reservoir water itself, then what would happen if you were to release a higher value? It would have, the reliable system services.
You use the word flashboards. Is it current practice to use flashboards on the spillway? And what are the increments and how much would that affect downstream flooding?
Flashboards, Peter.
Yeah, the flashboard, they're wooden flashboards. There's 2 wooden flashboards in each bay. There's 44 bays. So we can remove any one of those flashboards at any time. Like right now, today, we have 8 bays with no flashboards in them at all. So we're releasing water.
So there is no right and wrong rules here. They're like, like other, so we have flashboards here. What you said, like if you're looking at Massachusetts Water Authority, they have recently moved from using flashboard to be not wear. So, they're changing, but what it means is, like, as I said, like there's no right or wrong. And this is something that we are also evaluating what would happen, I mean, we do have numbers of like how much flashboard end up getting, like how much, like flow downstream.
There's an analysis.
There is an analysis, and Ground Water Supply also they have their Excel spreadsheet, a pretty easy one to show like what each flashboard mean in terms of water volume.
Thank you.
Thank you.
Thank you. That's a good question. So to me, it comes down to water capacity and what you have for available storage prior to a storm event. I know for March 2010, all our impoundments, we have the low-level outlets wide open, and it's literally like a drop in the ocean trying to how much past that water. So to me, if you can increase freeport capacity, I know it's not an inexpensive endeavor, that provides you more storage capability during these anomaly storm events that seem to be happening more frequently. Did you look at
Well, so
freeport capacity?
do you want to increase board capacity, or do you want to operate in a way like you leave a little bit? You don't need to have it fully saturated. That's another thing that we looked at, right? So it doesn't have to be at max. So how early can you release would be a question. So on anticipation of hurricane or tropical storm of certain strength, like Peter, they've already done, like they can contact National Weather Service and have this short-term river forecasting information and get some sense of like where reservoir would be given that inflow, and if you were to release water certain days ahead of the time when the flow is not, like the downstream river is not at backward, discharge state, that might be one of the things that could be done. And yeah, I mean, it's also possible that you increase the height of the board itself so that you can increase reservoir capacity. So those are, some of the alternatives.
I don't know the province, I mean, for our impoundments, we can't release, if we have storms coming, there's no way we can pass that much water before we, see it result in the dam. I don't know if the province has that ability or not. But
Yeah, John, we gauge the flow at the Cranston station and that ducts it with NOAA. So if we do see a storm events coming in, we try and release as much as we can downstream now since 2010. With their knowledge, so they can gauge it as well, and then we'll put the flashboards back in just before the storm comes in. They give us some freeport. But as far as adding more flashboards to the capacity of the reservoir, that would affect our operation of the gatehouse. We would actually be flooding the basement floor of the gatehouse where the gates are, and so we wouldn't be able to get in there and open up those gates if we added more flashboards. So that's probably off the table right now as far as adding more flashboards.
okay, thanks.
Thank you.
Thank you. Thank you.